Okay, any questions before I start? If not, let me first write it down. Lecture 5, and today is April 9th, 2021. All right. All right, so let's see where we were. Um, we were discussing your,
Professor,
yes?
just so you know, it's super out of focus.
Oh, let me, here we go. Is it good now?
Yeah.
Thank you for bringing that to my attention. So um, we are talking the modeling of uh, model of a structure as a single degree of freedom system. In other words, um, we want to set up this model for a complicated, or rather simple, or a little bit more, even more complicated structure. So far what we have discussed was we showed how you can use the lumbar force, which is the inertial force putting in the opposite direction, and the free body diagram, and use which gives you the equation of motion. And by you writing that equation of motion, you find a mass equivalent, K equivalent, or even C equivalent in a system. But most importantly, that helps you to identify the natural frequency. That's the ultimate goal. Now, we are starting the second approach, which is the direct definition of stiffness and uh, what I call using um, structural analysis. That's what we want to introduce. And I will introduce that in two phases. Phase one is when it comes to defining the stiffness, um, if you come across cases that you need to combine uh, different stiffness components. In this approach, you have different components to a system, so you need to combine these stiffness components. And usually identifying the stiffness or modeling the stiffness is the most difficult part of the problem. In combining these stiffness components, we come across a special case, which all books wrongly, they describe these special cases as springs in parallel or springs in series. I emphasize that a better description is that when the stiffnesses or the stiffness elements experience same force or same deformation. Because geometrically speaking, you may have springs that may seem to be in series, but they're actually experiencing the same deformation. So by this terminology, they're actually in parallel. Let me give you an example. Let's say you have a mass attached to two springs like this, K1, K2, and a beam here, which represents another spring. When this mass moves, which obviously causes a deformation to this beam, what happens? Beam, these two, all of them experience the same displacement. So although these are seem to be in series, They're not. In terms of the concept of a spring in series and um, parallel, which results into different outcome for the total effect of these stiffnesses or combination, that is not, these are not in series, they're in parallel. So that's why it is important to be careful with this terminology of series and parallel. But what I said was last time, if you let's start with two springs, okay, K1 and K2, and let's say both of these are subjected to the same force, okay? Obviously, they are subject to the same force, but because the stiffnesses are different, they're not going to experience the same deformation. The goal here is I want to find a single spring, equivalent spring, that would replace them, okay? Would be subjected to the same force. So spring one, K1, is going to what? Is subject to this same force, is going to experience this basically relationship, or the displacement that this spring will experience would be what? F over K1. For this one, the force is the same, but the displacement is different. So you have this relationship, right? So the displacement that spring will experience would be this, right? So if you replace these two with a single spring, but which obviously would experience this displacement, what is the relationship between this uh, replacement stiffness or equivalent stiffness and the force? You have K equivalent times U3 minus U1. So you can write the displacement that this equivalent spring would experience would be F over K equivalent. You see, if you add up these two, the left-hand side would be the same. In other words, you end up with F over K1 plus F over K2 would be the same as U3 minus U1, which means that this is equal to this. So from this, you get this relationship, which means if you have two springs or more springs, doesn't matter, you have n number of springs that are connected such that they experience the same force, you can replace them with a single spring that the stiffness of that can be obtained from this relationship. Okay? Now, what happens now if instead the springs experience the same displacement? Okay? Let's say you have two springs, I would start with two springs, that they're constrained such that when you have this force applied, they experience the same displacement. So, in other words, the total force that develops in these two is the applied load. And you can see that. Why? Because from the free body diagram, what you can write is this, right? So what is the relationship between the force in this spring and the deformation that it experiences? Would be K1 times U2 minus U1. How about this one? Would be K2 times U2 minus U1. Now, if you want to replace these two with a single spring, okay, which basically replaces these two. It will experience the same deformation. So this F would be what? K equivalent times U2 minus U1. Okay? So since F is F1 plus F2, you can simply write K1 times U2 minus U1 plus K2 times U2 minus U1 is equal to K equivalent times U2 minus U1. Therefore, in this case, the equivalent stiffness, in other words, a spring that can replace those two, would be sum of the stiffness of these two. Or if you have more than two, of course, again, they're all in parallel, like that example that I showed you, then you can just add them up. It is important to pause a little bit and think about the importance of detecting actually if you have the stiffnesses in a structure, stiffness components, are in parallel or are in series. And let me show you why it is important. Let's say you have a rotating machinery, okay, with all kinds of bearings that are supporting it, okay? This is a rotating machinery. Let's say you're an engineer, they hire you as a consultant to come and tell them, this rotating machinery is wobbling, we want to fix the vibration problem, okay? And you say, aha, I learned something good in my vibration course, so I can tell you what to do. I have detected this is the source of the problem. So you need to really strengthen this stiffness and make it much, much stronger. What happens if you had not done your homework and these bearings are experiencing the same force? So what you're telling these people is this, okay? Since you have not done your homework, right? You're telling them the problem is that you need to make this much stiffer. What happens? Let's say you would increase that stiffness to infinity, right? What happens? Contribution would be zero. So by stiffening that component, given that these bearings are all in series, you have actually made the problem worse. If the problem was that these were all in parallel, right? And you wanted to prevent the vibration by stiffening the system, obviously, okay, if they were all in parallel and you increase the stiffness of this, right? You're increasing the stiffness of the system. So natural frequency is K over M, right? So you're increasing the natural frequency of the system, which hopefully takes it away from the dominant frequency, which was causing the problem. So my point is that it is very important to recognize whether you have springs in series or in parallel by not falling into the trap that parallel means physically parallel, series means physically connected in series. So let me actually do this problem quick. Let's say you were given a problem like this. You have a beam connected, a lumped mass is at the end. This beam is supported by a bar with these geometric and material properties given. The beam has these properties, okay? And then you have another spring element, K. So again, as an engineer, somebody approaches you and say, okay, how can I replace this whole system of stiffnesses with a single stiffness, okay? Because I want to set up this model for the vibration analysis, and I want to find a natural frequency of this system. You look at this and you say, Professor Nuri told us that if you have a system that all the stiffnesses experience the same deformation, all of these, regardless of the geometry, which you should not be fooled by that, they are in parallel. Look, this beam is experiencing this deformation, and that is the deformation that both of these springs will experience. Therefore, what I have to do in order to find the equivalent stiffness, I need to find the stiffnesses of these three components and add them up. What is the stiffness of a beam, cantilever beam? You remember how you find the stiffness of a cantilever beam? We go by the definition of a stiffness. Stiffness means what? You want to replace this beam with a single spring, okay? Relationship between the force and the stiffness in a spring is what? F is K times delta, which means if this is 1, this will become the stiffness, right? So if you have a beam, you want to find its stiffness. In other words, this force is causing a deformation delta. What is that delta? That FL cubed over 3EI, right? So you have F 3EI over L cubed times that delta. This is your what? If this is displacement is 1, this is that is stiffness, okay? Which is 3EI over L cubed. How about for a bar with these properties? If this bar experiences a deformation delta, delta is what? You remember delta was, right? So if this is 1, this would be the stiffness. So stiffness of a bar is AE over L. You should remember these from the strength of materials. So in this case, the stiffness of the system would be for that beam, which is 3EIL1 cubed, okay, right? I'm sorry, 3EI over L1 cubed. For this bar is AE over L2. And for this spring, of course, that was given. So you can replace this, all of these with a single spring and not being fooled by the geometric configuration. Another example, if you're given a shaft, a non-prismatic shaft, okay, which is experiencing vibration. So all the properties of each shaft is given. L1, G1, J1, L2, G2, J2, and this is vibrating. You don't like this. You want to replace it with a single shaft or a single torsional spring, meaning that you want to replace this whole thing with something like this. That's the idea. That's we are talking about modeling, right? So what do you have here? If this mass at the end of the beam is subjected to a force, what can you tell about these two? Obviously, of course, a torque, right? These two would experience the same force, okay? That means These two are in series. What is the stiffness of a shaft? Go by the definition of the stiffness. Angular deformation due to torque is TL over GJ. What is the stiffness? Which is the torsional stiffness here. Torque that causes unit deformation. So torsional stiffness is GJ over L. So for this system, you write 1 over K equivalent is 1 over KT1 plus 1 over KT2, where KT1 is what? G1, J1 over L1. KT2 is G2, J2 over L2. Okay? And substituted here, you find the equivalent stiffness. This is different. Would have been a completely different problem if you had a shaft like this. If you had a shaft like this is the mass and is rotating. What can you say about these two? This is similar to this problem. In fact, you have this in the homework, that this being displaced, right? These two seemingly are connected in series, but they're not subjected to the same force. They're subjected to the same deformation. And that's what it is here. Because all you can say here that they experience the same deformation. I don't know what the forces are in these two. It's an indeterminate problem. I need to figure that out. But all I know that they're subjected to the same deformation. Therefore, in this case, K equivalent would be sum of these two. Okay? Any questions? Okay,
Yeah, Professor, I have a question.
sure.
So just to clarify, if they're subject to the same force, it would be series, and if they have the same deformation, it would be parallel.
Exactly. Exactly. That's what I want you to remember and not fall in the trap of this business of series and parallel.
Okay.
Same force. Yeah, great. All right. So now let me do, I like to actually go over some interesting problems that some of you have asked me about. They're part of the homework set that you've been assigned, but I really like to give you a good hint by going over specifically those two problems, because they are very interesting. And I intentionally assigned those because they're rather sort of a complicated problem, but it really helps you to grasp a good understanding of what is the meaning of series and parallel, or what is the meaning of springs experience the same force or the same deformation. So I will start with this problem. There is a shaft, a non-prismatic shaft, okay? You have a disc attached to it here. This is a disc with mass M. And the shaft has these pieces, each one okay. Now, the stiffness of each piece is given. These are torsional stiffnesses, but that's, not the point. So the torsional stiffness of each piece is given. This disc is also connected to two springs with the given stiffnesses, K5 and K6. So the problem is basically asking you if this is subjected to an external force, M of T, is asking you, can you set up this model for this system? Just in time, okay. All right, so can you set up the, I have to apologize, I gotta admit one person here. Well, I don't know what happened, but anyway. Okay, so this is the question. How can you model this system as a single degree of freedom system like this? Let's pause and look at this problem. Um, you look at this, you see that immediately you can see that this, and this, if you have a force applied, this is the disk, to this shaft here, what can you tell about these three? They experience the same force. I don't know what each individual force is, but nevertheless, they would experience the same force. So you can immediately say that these three are in series. So how do I find the equivalent stiffness for that? I can write 1 over K equivalent 1 is 1 over K1 plus 1 over K2 plus 1 over K3. So I can find the equivalent stiffness for that. So the problem now is reduced to this problem. The problem that we have is now reduced to this problem. You have K4, you have this disk, and the radius of this disk is given as R is going through some angular rotation theta. Okay, so now you have this problem. So now what about these two? And of course, you have these springs as well. So what happens when you have these two shafts in with this orientation, with a disk in the middle that is going through some rotation? You can see that these two are in parallel or series. Do they experience the same
Parallel.
force? Parallel, because they are experiencing the same deformation. You don't know what the force is in these two. They're fixed on the two ends, and so this is an indeterminate problem. I have no idea what these two forces are, but I can tell you that if these two are constrained like that, these would experience the same deformation. So therefore, I can replace K1 and K4 by K equivalent 2, and that would be K equivalent 1 that we found earlier plus K4. Okay? So now the problem is further reduced to this. I have a single shaft with this stiffness attached to this disk, which is experiencing this moment, and it is, of course, you have these two springs attached to it, K5 and K6, right? As this is rotating, right, what would be the experience that these two springs would go through? Do they experience the same force or the same displacement? I don't know.
Displacement.
The same displacement, exactly. I don't know what force they would experience. So these two then are in parallel, and I can replace those two springs with a single spring whose stiffness would be this, right? So the problem now is further reduced to this. K equivalent to a disk that is supported by this K, this is spring, and is experiencing this moment, which is causing this rotation. Now, how can I replace these two with a single spring? Okay, this is what I would do. This is what I would do. If you look at this rotation of this disk due to this moment, okay? This moment is due to, as this is rotating, you can, from the equilibrium, say that the moment, external moment, is the sum of the moment that this generates plus the moment that this disk and this shaft will generate. Okay? What is the moment that this K equivalent to will generate? That moment, or let me call that M2, would be what? Would be K equivalent to, which is a rotational spring, right? Times the angle of deformation, right? That's that moment. But how about the moment that this force generates? What is the moment that that force generates? If you look from the top, this spring represents a force. When it deforms, a force is generated in this spring, and it is that force that is developing a moment. We are talking about summation of moments about this point, right? That's what we were doing. Summation of the moments about point O, which is this external, equal to the external moment, is sum of these two. So this is the moment generated by that torque, by that shaft. How about this one? This would be perpendicular, obviously, to this at the radius r. So that moment would be that F times r. But what is that F? Would be the force due to deformation of that spring, which we call that is the stiffness is K equivalent 3. But what is the deformation that this spring is going through? If this is theta, this is the deformation that this is going to go through. In other words, if you look at this, this is delta, looking at this angle, radius r. So that deformation, this deformation is what? Is K equivalent times r times theta. Okay? So the moment that this generates is F times r. Therefore, the moment of that spring that generates about point O would be K equivalent times r times theta times r, or is K equivalent, that we call it 3, times r theta squared. Okay, so the total force moment, which was the sum of these two, is K equivalent 2 plus K equivalent 3, right? R squared times theta. Okay? So this is the moment, right? That is causing this deformation. Look at this equation, compare that with this. What is this? This is the total stiffness. So the total stiffness then would be K equivalent 2 plus K equivalent 3 times R squared. Of course, you need to substitute for these values. K equivalent 2 was the equivalent stiffness we found for this, which was K equivalent 1 plus K4. This was K equivalent 1. I didn't substitute those. You can do that and find the actual final answer, but that's how you solve that problem. I knew that this would be an interesting problem, so I thought, it's important to give you at least a hint how to do that problem. Any questions?
Yeah, could we go over the first part of this problem?
Absolutely, sure. Which part? This here?
On the first equivalent spring, I don't understand that part.
See, let me actually show you this. Let me demonstrate it here, because the problem may be a little bit complicated. Let me show you this. If you had a shaft like this, which is what we have here. This is K4, this is K3, this is K2, this is K1, okay? This is the disk. So as this thing is rotating, right? Or subjected, in other words, to a moment, right? Or a torque. What can you tell about these three? These three, go back to the strength of material, will be subjected to the same force, right? Won't they? That's all you can say. Instead of this, let me actually look at something even more simple. Let's say you have a shaft like this, subjected to a torque. You do know these two obviously experience the same deformation, right? These two.
Yeah.
But as far as this is concerned, the whole piece is subjected to one force. It happens that this piece is made of these three components, right? So what I'm saying is all of these components experience the same force. Since all of them experience the same force, the concept of summation of springs tell me these are in series. That's how I came up with the equivalent stiffness for these three. Does that elaborate?
Yeah, that makes more sense. And then also at the end, when you found the final moment,
Yes.
I'm a little confused because I understand how we got it, but it doesn't look like the units would make sense.
Oh, you mean here?
Now at the very end, we have K, like at the very,
Where did I put? Oh, this one?
yeah,
The unit do make sense because remember, this is, let's say, pound per inch. This is inch squared, right? This one is actually pound inch because it's rotational spring.
okay. I
And
see.
so it would be also pound inch. So if you substitute that, yeah, seemingly, because I'm using the same notation, may not look right, but this is a torsional spring, this is a torsional spring, and this is a torsional spring. But good observation, I appreciate that. Thank you for that.
So,
Okay,
sir, I have another question.
please.
How did you know that the springs were connected tangent to the disc, the two linear springs, and not like connected straight to it?
You mean these two springs?
Yeah, because if they
That's
were at a different angle, I'd think it'd be different, wouldn't it?
good point. Yes. Well, this is what the book actually shows, or the intention of the problem is. that, let's say, this is what you're saying is, and you have a very good point also. You're saying that, okay, if these are connected, not tangent, but with an angle, right? That's what you're saying, right? If the angles are, if these are all, they all go back to the assumption that the angle of rotation is very small. So what you're saying is this, if I had two colors, again, a very good point. What he's saying is this, okay, the disc is experiencing this deformation, but the spring is going to experience, if this is going that way, right, the spring would go here. So would experience this deformation. So how can I claim that these two are the same? That's your question, right? Isn't that
Well,
what you,
I'm also just asking, how did you know that those two springs were tangent to the disc there? How did you know they didn't just come straight into the disc? Or were connected at an angle relative to the disc or something?
I
oh,
think
re-
in
regardless whether they're, that's what my point is, regardless if they're coming tangent or in an angle, as long as this is a very, very small angle, the deformation of this would be the same as L or theta. But your point is that, I see what your point is, that, okay, why you're considering the force of this being tangent to this, right? That's what your question is, right?
Yeah.
So, yes. Again, uh, since the angle is very, very small, we are making the assumption that, okay, at this point of connection, if you're experiencing a force, this angle is negligible. So it is as if this spring is actually connected tangent to the disc. And if I'm not mistaken, in the drawing of the book, actually shows that the two springs are attached tangent to the disc, if you look at the problem statement. Very good question. I'm glad you asked that. Before I run out of time, I want to also do another interesting problem, which I did in the other section, and that is problem 2.7. This is also a very interesting problem. This is what you have been given. You have a rigid beam supported by two springs like this, K1, K2. This is at a distance L1. This is at a distance L2. And then at the tip of this beam, you have another spring that carries a mass, and it is connected. And the problem, again, is asking you basically to model or set up this model for this system. This is very similar to the problem that I just did. How? In doing this problem, solving this problem, you use the concept of equivalent systems. Do you remember that in statics, concept of equivalent system? Concept of equivalent system was what? If you have several forces acting on a system, you can find a force, and you can move these forces to any point you want, right? As long as the moment that the sum of these forces that you put at that point, okay, generates about a point is the same as the sum of the moment of those individual forces about the same point. This was a concept of equivalent system. So we're going to use that concept. How? What I would say is this. This is a rigid beam, of course, massless, as the problem states, and it's going through this rotation, okay, theta. As this beam is going through rotation theta, this spring is going to generate a force F1. This spring is going to generate force F2. I want to replace these two with a force that is here. Okay? The reason is I want to actually replace these two springs with a spring at this point, because that's going to make my life easier now, because that spring and this spring are in series. How do I do that? I would say, if I want to replace these two with a spring that is attached here that would replace these two, the moment that this force that is caused or developed due to this spring about this point O would be the same as the sum of the moment of these two. In other words, F1 times L1 plus F2 times L2 should be the moment of this guy about point O. You follow me? Simple concept of equivalent systems. But what is F1? Remember that these are the displacement that each of these, if this was coming from a spring, which we are looking for, I call that K equivalent prime, okay? F3 would be K equivalent prime 3 times L3 theta, that's this displacement. F2 would be this displacement, delta 2, which is K equivalent, K2 times this delta, which is L2 theta, okay? And F1 would be K1 L1 theta, right? So put these in here. You have K1, if you substitute here, would be K1 L1 squared theta plus K2 L2 squared theta, and this is equal to K equivalent prime L 3, right? Squared theta. Thetas cancel out. So K equivalent prime that I'm looking for would be K1 L1 squared plus K2 L2 squared divided by L3 squared. So what I have done, I have converted this problem to this problem. I have a beam, rigid beam, okay, that has a spring K equivalent prime attached to it. Then I have this spring, which is attached to a mass. So how do I find the equivalent stiffness here? This is easy now, right? These two are in series. There is no mass here. This is massless. So you have just a point connection of these two springs. Okay? So K equivalent would be 1 over K plus 1 over K equivalent prime. And then you have replaced that whole problem with this model. Any questions?
Could you go
Can
to
you
the
show
page
the
before
last
that?
page for a second?
Absolutely. Sure. Here. Oops, sorry. Here we go. So, any questions? Let me see. There are two questions in the chat. In the diagram of the problem statement, there is a black dot where it attaches that, indicates that it connects tangentially. Okay, good point. All right, this is related to the problem with those two springs, the disc. Thank you for the clarification. Okay, no questions? So we are done. Have a wonderful weekend.